Knowing how to find critical numbers, or critical values they're sometimes called as well, is a very important application of derivatives in differential calculus. It's so important because it's the kind of initial step of a lot of different types of problems that kind of build on top of that in calculus. So in this video, I wanted to show you an example of using derivatives to find the critical numbers or critical values of a given function. Do keep in mind though, although I'm talking about one specific example in this video, I am going to go over strategies that come up in other types of examples, just kind of a general strategy that you want to keep in the back of your mind as you work through other problems. So by the end of this video, you should feel a lot more confident with applying the techniques I talk about in this video, not just to problems that are super similar to the one that I'm going to be going over, but to pretty much any function that you're going to want to find critical numbers of at some point. If that sounds good to you, be sure to stick around to the end of the video, and without further ado, let's go ahead and jump right into it. Find the critical numbers of the function f of x equals x cubed plus 6x squared minus 15x. So first question here, when you're looking at a problem like this, what is a critical number? How do you find a critical number? Well, a critical number occurs in two places. There's really two conditions that can be met in order for a specific x value to represent a critical number of a function. Two things to think about. First of all, a critical number will occur wherever f prime of x equals 0. So in other words, if you take the derivative of your function and set it equal to 0 and solve for x, whatever x value makes this equation be true is going to be a critical number. Okay? The second condition that can create a critical number is wherever f prime of x does not exist. So that's kind of a common one that people miss. Not only can you create a critical number, or I should say find a critical number, at a place where the derivative of your function equals 0, but also where your derivative does not exist. So if you have some function where you take the derivative and then there's some x value where that function would not be defined, like for example, if you find a situation where you have a fraction, your derivative is a fraction, and some place where x makes the denominator equal 0, you're dividing by 0, your derivative would not exist there. So that's just one example. There could be other things that could create that, but these two things are what we want to look out for. So in other words, well, I guess not in other words, but the first step when you're trying to find the critical numbers of a function, it's always going to follow the same process, right? So the first step is always going to be find the derivative. Obviously, both of these conditions require us knowing something about the derivative of the function. So you're always going to start by finding the derivative. So let's go ahead and do that first. In this case, this function can be found, the derivative of this function can be found simply by using the power rule. So we can bring our power down in front and then lower our power by 1. So that gives us a 3 down in front, leave our base x as x, and then minus 1 from the power. 3 minus 1 is 2. Okay. The derivative, again, of this term will be found with the power rule. So we can bring our 2 down in front. 6 times 2 is 12. Leave our x as x, subtract 1 from the power. 2 minus 1 is 1. X to the first power is the same as just x. So I'm not even going to put that there. And then minus the derivative of 15x. The derivative of a constant times x is always just going to be whatever that constant is. So it's going to be minus 15. Okay. So here's f prime of x. Here's our derivative. So let's think about each of these two conditions where critical numbers could arise. First place is going to be where f prime of x equals 0. So if we take our f prime of x and see where it equals 0, that should tell us where our critical numbers are. Okay. The other place would be where f prime of x does not exist. Well, let's look at this function here for a second, because not all functions are going to have x values where the function does not exist. So this may not be applicable, but you always want to consider it just in case. So in this case, we have a polynomial, right? Some coefficient times x to a positive integer power. Some coefficient times x to a positive integer power. Or a constant, like in this case. So all the terms here are basically having, I should say, having the sum or difference of a bunch of terms that kind of have this format where you have a coefficient times x raised up to some positive integer power. That just means a positive whole number is going to be a polynomial. So this is an example of a polynomial. Well, polynomials exist for all x values. That's just kind of a property of polynomials. Therefore, this, in this case, is not going to have any, we're not going to get any x values from this second condition here. F prime of x exists for all x values. There's not going to be any places where this does not exist. So this is really the only thing we need to worry about in this case. Where does f prime of x equal 0? Well, we could figure that out whenever you have a polynomial equaling 0 and you're trying to solve for x. Typically, the best strategy there is going to be to factor out that polynomial. Well, in this case, we can do that. This polynomial is going to factor out, and it's actually going to factor out to 3x minus 3 times x plus 5, right? You really just want to think about kind of what, well, I'm not going to get into kind of the full process of factoring in this video. That would be a topic for another video perhaps, but we can kind of reverse confirm that this works if we think about foiling this out. 3x times x does give us 3x squared, okay? And then 3x times 5 gives us plus 15x, minus 3 times x gives us minus 3x. So 15x minus 3x does give us 12x. And then finally, negative 3 times positive 5 gives us negative 15. So this kind of factored out version is equivalent to this foiled out version. So when you have two factors like this and you know the product of those two factors equals 0, what you can do is split this into two separate equations, because if anything times 0 is 0. So if this piece equals 0, then the product of those two things will also equal 0. Similarly, if this piece alone equals 0, the product of these two things will equal 0, because we'd have some other number times 0. So we can kind of split this into two separate problems, okay? And then we can solve each of those on their own. So in this case, we can add 3 to both sides. 3x equals 3, divide by 3. X equals 1. And in this case, we just need to minus 5 from both sides. X equals negative 5. So x equals negative 5 and x equals 1 are going to be the two critical numbers of this function that we had up here. Well, I hope you're feeling a bit better about how to find critical numbers after watching that. I think you'll also get a lot of value out of my weekly live streams, which I typically do every Monday night at 5 o'clock Pacific time, where we go over different calculus topics, examples, and you can even throw your questions in the live chat and get some help with homework or whatever other questions you have answered live. If that sounds good to you, just hit that subscribe button down below and that bell icon as well so you're notified when I go live next week, and hopefully I'll see you there on Monday.